Now we're going to talk about 2D kinematics. My simple definition of 2D kinematics is keeping up with x and y motion. It's really not that different from 1D kinematics. We just now have 2 dimensions to keep up with. Our demo of 2D kinematics is to have a ball roll on a 2D plane, and then we'll plot it and do the equations like we always do. Now Hal was supposed to do this, but Hal's a little bit of a prima donna. He said something about rust marks starting to show up, and he kind of freaked out. So this is one of the plastics who you're going to meet later is going to do it. So the plastic is going to start at a little bit of an offset on the y-axis and then just kind of go like this at a nice uniform smooth motion. So let's make a plot of that here. So plus y plus x. So this is not a kinematics plot, this is a trajectory plot. And remember, started out a little bit up on the y-axis and moved kind of like that. That's the actual path that the ball took in x and y, something like that. So if we were to catch it at snapshots in time, something like this. Equal displacements with equal amounts of time. So how do we treat the kinematics? What do we do? It's very simple. You treat x and y separately. Good Lord. There we go. Treat x and y separately. Since they're not coupled, since the x position doesn't affect the y motion, and since the y position doesn't affect the x motion, it's like 2 separate motions happening at the same time. So if we wanted to, we could even do the kinematics completely separate. We could make a plot of the y versus time, and we can make a plot of the x versus time. Let's see, y had a little bit of an offset and went at some slope. X, we started at the origin, but the slope was actually higher. I kind of had it moving a little faster in x than I did at y. So that would be a reasonable plot. And since it was at constant velocity, we could do constant velocity kinematics. If we wanted to, we could say, well, delta y, we could say y final equals y initial plus v yt. We could keep up with where it is on the y-axis at all times. And we could say x final equals, actually, there is no x initial, so I'll leave that out. Right, this one had a y initial and this one doesn't. So x final equals v x t. You could do them completely separate, and that's one way you can do it, but actually in the next board I'm going to show you how to do it a little bit more sophisticated. It's actually better to keep it all together, so we'll show you that next. But in principle, it's just 2 separate motions. Let's look at a more mathematically sophisticated way to do 2D kinematics. We're going to do it in terms of the position vector r. So an r with a vector hat, which equals the displacement from the origin. From the origin. Remember when someone asked earlier, why is position a vector? Because position is really displacement, it's just displacement from the origin. R does not mean radius. It has nothing to do with a circle or circular motion or a sphere, anything with a radius. As you go further in physics, you'll find R is just the general vector used to describe position when it could be along X or Y or anywhere in space. So let's look at what do we really mean by that. So let's draw a couple of R's. Well, it's simply the vector from the origin, here's the origin, to a position. So our initial one is right there. There is Ri. Write that bigger. Ri. So let's consider 2 positions, where it started and where it ended, right? R initial, R final. So for our final, let's say, really it can be any of these. Let's just pick another point along the motion. Let's say here. So now I'm going to draw, there's our final. I'm drawing them nice and heavy so you can see them. Whoops. Right, that's our final. And in general, there's nothing mysterious about these. R really is just x I hat plus y j hat. It's just where you are in the x and y axis, just drawn as a vector from the origin. But I want to show you how this actually makes sense when you put it together to get the displacement, or to get delta r. Right? So let's look at these two positions. Now let's draw them on top of each other here. So here is our initial, and here is our final. But we want to get the change, delta r. Right? So delta r is what? Delta r is the displacement, r final minus r initial. Just like delta x was the displacement, x final minus x initial. Right? So if we want to vector add these but subtract them, you would say rf and then you would add ri, but you'd flip it over. You'd make it go negative. Right? So ri is basically going to be like that. That's negative ri. Right? And then vector add those and it looks like this. Right? That is delta r. That's rf minus ri. There it is right there, delta r. And you look at it, and what does it look like? It looks like the vector here. See, delta r is along the path. It's just the vector going along the path. It's the delta x. It's the same. It's just the generalized x and y displacement vector for a change in position. So we didn't move from the origin to these two places. We moved from this place to this place. Delta r is just a way to get a vector that goes from the initial position to the final position. If you wanted to, you could write it out in all of its glorious components. Let's do that just to make you feel better, just for fun. If this seems weird and unusual, you could write this as, for the x components, it's x final minus x initial I hat plus y final minus y initial j hat. Just like the position vector is just x I hat and y j hat. It's just a more compact way to write things. And it's nice because now we can just use the 1D equations with r hat if we want to, right? So we can say just like 1D, and now we can say things like, well, the 2D, if we have the velocity anywhere in a two-dimensional plane, the average velocity is delta r over delta t. And the instantaneous velocity in a plane v is dr dt. So those are some good kinematics equations or definitions that you could use to derive kinematics equations. And in this example, then, if we wanted to write out the kinematics, you would just apply the kinematics you know from 1D into the different components. Right? So what we would do, the main thing you're trying to do is we move forward into trajectories. If you can write the equation for r, you're done. You can solve any problem. So let's do that. Let's write the vector equation for r. r is the position at any time. Right? So the x component, we just think about x kinematics. Right? This thing is moving. Its velocity has an x component vx and a y component vy. So we say in the x, we have constant velocity motion with no initial displacement. Right? So it's x initial plus vxt. X initial is 0. So it's just vx times t I hat. Right? That's the x component of r, the position. And in the y, it does have an initial position. Y initial plus the y component of the velocity times t, like that. And remember, those components are like this. This is x, y. We could draw the velocity like that. It has an x component and a y component. That's what vx and vy are. Once you have this, you can do lots of things. What's the velocity vector? Oh, that's easy. Just take the derivative. The derivative of this, vx times t, the derivative of that is just vx I hat. What's the derivative of this? Derivative of that with respect to time, 0, vy j hat. That had better be the velocity vector, right? In this case, that's very straightforward. What's the acceleration vector? Take another derivative. 0, plus 0, 0. There is no acceleration, right? This was uniform motion. So get used to using r. I'm going to show you how if you can find r, you're done. You can solve any problem.